Hello everyone, this is chapter 2.1 and in this lecture we'll be looking at our first family of organic compounds, hydrocarbons. In addition, we'll be discussing polarity in terms of polar bonds and molecules. We'll be looking at the different types of intermolecular forces that can exist between molecules of organic compounds, and finally we'll be considering some physical properties, particularly solubility and boiling point. This lecture will be broken down into a sequence of 5 videos, one for each topic as shown. However, your handout as usual contains the slides for the whole lecture sequence. The videos are addressed as per the topics here and will be referenced in your handout accordingly. The hydrocarbons, unsurprisingly, are compounds that only contain the elements carbon and hydrogen. Nonetheless, there is a diversity in families of organic compounds that consist of just these two elements. The first organic family of compounds that we're going to look at are called the alkanes, and here are two representative members, that's methane and propane, shown in a variety of different views. See if you can recap what some of these representations are. Pause the video and resume when you are ready. Okay, so each member of this homologous series of acyclic, it means that they're not in a ring, linear, which means that there's no branching, contains an addition of a successive methylene group, and methylene groups are just CH2 units. All of the carbons in this family of hydrocarbons are sp3 hybridized and adopt a tetrahedral geometry around each carbon atom. You might hear these as being referred to as saturated hydrocarbons. This simply means that the carbon has formed the maximum number of bonds around its atoms and has 4 bonding groups. It is possible to calculate the molecular formula from a general formula, which is CnH2n plus 2, where n represents a whole number greater than 0. So as a practice, if you can calculate and draw the bond line formula for the following straight chain alkanes, so one that contains 5 carbons and the other will contain 22 hydrogens. Pause the video and press play when you're ready to resume. Okay, here is the answer to the molecular formula that contains 5 carbons, and here is its bond line or skeletal formula. Here is the answer to the molecular formula that contains 22 hydrogen atoms, and here is its bond line or skeletal formula. Other cyclic alkanes with the same general formula include the branched alkanes, but these are constitutional isomers, which we'll discuss in a later video. On this slide, we're going to talk about cycloalkanes and other cyclic compounds that you will encounter on OChem 1. So these usually take the form of regular polygons. The most commonly cited cycloalkane is cyclohexane, and all of its atoms are sp3 hybridized. However, it's worth noting that cycloalkane rings with fewer than 6 carbons deviate from the tetrahedral bond angle. A whole chapter is dedicated to the study of cyclohexanes, but for now we'll recognize that their general formula is the same as that of an alkene, which we'll talk about on the next slide. Note that we use the bond line skeletal formula to represent these just as we do for regular acyclic hydrocarbons. This means that we just leave off the hydrogens. The general formula of a cycloalkane is given as CnH2n. Another interesting cyclic hydrocarbon is benzene, and this will be studied in a great deal of detail in OChem 2. However, for now, it's sufficient that you know that only rings of this type we will be referring to as aromatic on this course. Each carbon is sp2 hybridized, and it has the unique molecular formula of C6H6. So here's a couple of tasks for you to do. See if you can draw the shape of the following cycloalkanes. That's a cycloalkane with 3 carbons and one with 5 carbons. Pause the video and resume when you're ready. Okay, so here is the molecular formula and the bond line formula of cyclopropane. This is a cycloalkane with 3 carbons, and here is the molecular formula and bond line formula of cyclopentane, a cycloalkane with 5 carbons. As mentioned before, the alkenes have the same general formula as the saturated cycloalkanes. This is CnH2n. We've already seen the different representations of this second family of hydrocarbons, and their sp2 centres provide a rich chemistry that we'll be exploring in future chapters. The alkenes all have trigonal planar geometry and are unsaturated, in that these carbons typically have only 3 groups surrounding the sp2 centre, where the atoms are connected by a pi bond. This is also the first family of hydrocarbons that demonstrate a specific type of stereoisomerism, cis-trans isomerism. Here I have only shown you one example of an alkene. For alkenes with greater than 2 carbons, the double bond can feature in different positions. Try and draw all of the possible constitutional and configurational, that's cis-trans isomers of an alkene that has 4 carbons. Pause the video and resume when you are ready. Here are the possible constitutional isomers. Note how the double bond can either be between carbons 1 and 2 or 2 and 3. If you drew one between 3 and 4, then this is not unique, as it has the same connectivity as atoms where the double bond is between carbons 1 and 2. Build 2 models and see this for yourself by rotating and superimposing one structure on the other. This means that the structures will be identical. So the other isomers are the cis-trans isomers, and these are displayed here. Here is the third representative member of a family of hydrocarbons known as the alkynes. These two are unsaturated hydrocarbons, as the carbon only has 2 bonding groups surrounding them. The general formula for each successive addition of a CH2, that's methylene unit, is CnH2n minus 2. Alkynes contain sp hybridized carbon atoms with a linear geometry. Please respect this linear geometry when you draw any bond line or skeletal formula. To emphasize this, I've included neocosinostatin chromophore A, and this is an anti-tumor antibiotic used for treating patients that have liver cancer. There are at least 3 different hydrocarbon skeletons that this drug is based upon. Can you identify the hydrocarbon-based skeletons? Pause the video and resume when you think you have an idea. There are a number of possible answers, but some include the aromatic rings at the left of the molecule. There's a cyclohexane ring that's disguised in a conformation we'll be learning about in future lessons at the bottom of the molecule. And of course you could have indicated the alkenes, both of which are part of ring structures, and of course the alkyne groups. Again, note the importance of the geometry for each sp3, sp2 and sp hybridized atom. In this video we're going to talk about bond polarity, but before we do this I wanted to recap some ideas that you studied in Modern Chem 1. First, let's have a look at the bond dissociation enthalpies of common carbon-carbon bonds and recap their hybridization. Now, these bond dissociation energies that are displayed on this slide indicate the energy of dissociation. So these will produce carbon atoms that contain the unpaired electrons that they shared when they were forming these bonds. So for example, to form a carbon-carbon single bond, each atom contributed 1 electron for each carbon-carbon single bond formed, whereas in a carbon-carbon double bond, the atoms overlapped with 2 electrons, and so on. In order to understand these energies, let's use the molecular orbital diagrams and consider the carbon-carbon double bond more specifically. This will give us some insight about the high bond strength, but also the high reactivity of this particular pi bond. Here we see the sp2 hybrid orbitals of each carbon atom and how they overlap to produce the sigma bond first. Now this will require at least 338 kilojoules per mole of energy to break that bond. Now notice how correspondingly it's lower in energy on the diagram. And this corresponds also to the picture which shows from the sigma bond being formed the excellent head-on overlap of its 2p orbitals. It stands to reason that more energy would be needed to break this bond. The double bond, however, consists of a sigma and a pi bond, and if we also remember from our molecular orbital diagram, the pi bond results from this sideways overlap of two 2p orbitals to produce a pi molecular bonding orbital with an electron density that's both above and below the sigma bond. Now firstly, this overlap is weaker as indicated by the lower energy required to break this bond, and this also goes some way to explaining the reactivity. It's only the pi bond that's going to take part in the reaction. The sigma bond usually remains intact. Whilst the carbon-carbon double bond's really strong, what we're saying by our bond dissociation enthalpy is that you have to break both of these bonds. That's the 610 kilojoules per mole, and this is why we see some incongruity between the high bond strength and the high reactivity. So that kind of, I hope, explains that idea. Students often think that the bond order and bond lengths are at odds with the increase in reactivity when we go from carbon-carbon sigma bonds to carbon-carbon pi bonds. Remember also that carbon-carbon double and triple bonds are comprised of individual components, and in a reaction these are not usually all broken at the same time. They're broken in a stepwise fashion. When we compare atoms of the same type, we relate bond order, bond length and bond strength, as we did when we looked at molecular orbital theory back in Modern Chem 1. So as a quick recap, when the bond order, that's single equals 1, double equals 2 and triple equals 3, increases, then there's going to be a better overlap of the carbon atoms on the whole, and this will mean there is a shorter bond length and consequently more energy required to completely dissociate that bond, thus producing carbon atoms that contain the unpaired electrons from which these bonds were comprised. Now, what if we have two different atoms connected? Well, let's consider the overlap of an sp3 hybridized carbon with the halogen atoms as we descend group 7. Seeing as the bond order of all of these bonds is 1, there are different factors that affect the bond length and strength. The one thing that is in common with the previous slide is the concept of orbital overlap. The better the orbital overlap, then the shorter the bond and the greater its strength. However, the electronegativity and the sizes of the halogens to which the carbon atom is bonded now need to be factored into this discussion. As expected, the carbon-fluorine bond has the highest bond energy, and this is because it has the best overlap of its orbitals. We can make sense of this by thinking about the atomic size of each atom and the attraction it has for the bonding electrons, particularly for fluorine. As we descend group 7, we should observe two things. 1, the atomic sizes of the halogens increase, and 2, the electronegativity decreases. This follows as the more shielded bromine atom would have far less attraction for the bonded electrons and a worse overlap of its orbital with carbon. A question I now want you to consider, though, is which is more reactive, the carbon-fluorine bond or the carbon-bromine bond? Pause the video and resume when ready. The strong overlap means that the carbon-fluorine bond requires more energy to break, and so carbon-fluorine compounds aren't particularly reactive, and so it's difficult to transform this bond under mild conditions. However, the carbon-bromine bond is weaker because the overlap of the bonding orbitals between carbon and bromine is weaker. This is reflected by the longer bond length and the lowest bond energy in this bond series. This is most frequently the carbon-halogen bond that is used for transformations. So it's not always about the greatest electronegative atom. Reactivity is nuanced by a deeper understanding of periodic trends. Nonetheless, let's see if we can expand these ideas to explain the reactivity of another very important bond in organic chemistry. That is the carbon-oxygen double bond, also known as the carbonyl bond. The carbon and oxygen atoms have a good overlap due to their similarity in size, but the carbonyl bond is much stronger, yet much more reactive than the corresponding carbon-carbon double bond. Take a few minutes to think about why this is, pause the video and resume when you're ready. So the electronegativity difference here is hugely important. We also need to think about where the electron density is on our reacting atoms. Every molecule has a highest occupied molecular orbital called a HOMO and a lowest unoccupied molecular orbital called a LUMO. The HOMO of one molecule can overlap with the LUMO from a different molecule and form a new orbital that is lower in energy. The pi-bonded molecular orbital is the same shape as ethene's, but the electron density is shifted towards the oxygen atom. Notice how the antibonding pi star molecular orbital, this is the LUMO, now has a larger lobe on carbon, and this makes it a target for electron donation by other atoms. Once this overlap occurs, then the new bonding orbital that results is lower in energy. The key takeaway here is that a stronger bond does not always mean a lower reactivity. The strength of a bond and where its electrons are located also need to be considered. Now let's think about bond polarization. Now we've talked about the molecular orbital theory. Of course, we don't always represent the polarization of bonds using molecular orbitals. We often do this using the partial charges to indicate the nature of the bond and to reflect its partial ionic character. Typically, we use bond dipoles to do this as indicated in the diagram. We might say that the bond is stronger because of the increased attraction of these two atoms and the polarization of the bond, but remember, the reactivity results from the ability of the LUMO of one molecule, that's the carbonyl, to overlap with the HOMO of another molecule, thus forming a more stable bond. And this is the effect of having a polar bond. However, simpler pictures help us just to see how the atoms align so that the reactions between these molecular orbitals can occur. Let's take a look at an example now. The teardrop shapes on each of these molecules represents the electron density distribution of the bonded atoms. It's possible to predict how these atoms will align with each other, and this is a useful exercise ahead of drawing mechanisms. Pause the video and see if you can predict how these two molecules will align with each other. Okay, so here is the answer.
This concludes part B.
In this video, we're going to determine whether a molecule is nonpolar and then whether a molecule is polar. So let's first consider the nonpolar molecule, that's carbon tetrachloride. First, we know that all of the bond dipoles, they are polar, and this is because of the difference in electronegativity between the carbon and chlorine atoms. But despite having these polar bonds, we've already said carbon tetrachloride is not a polar molecule. So why is this? Well, we need to think about the sum of all of the bond dipoles. Because this is a symmetrical molecule, all of the bond dipoles cancel, as there is no overall direction that the electron density is being pulled towards. This is why shape of molecules is just as important as knowing whether or not it contains polar bonds. Needless to say, if a molecule contains no polar bonds, then it can't be a polar molecule. Think of methane, CH4. there isn't enough of a difference in electronegativity between the carbon and hydrogen atoms, and so this is a non-polar molecule. Now let's think about some molecules that are polar. There are two conditions by which we'll consider whether a molecule can be polar. The first is easy because the molecule must contain polar bonds. That's a given. But the second condition is based upon how these polar bonds are arranged around a central atom, i.e. the molecular geometry of that atom. And so this will be the main factor in determining whether there is a molecular dipole, so whether the electron density is shifted in one overall direction. And this is what we mean by the sum of the bond dipoles. In the first example, the bonding dipoles are towards the chlorine atom, but the molecular dipole is also going to be in that direction as well, and this is because the carbon-hydrogen bonds are non-polar. In the second example, water, the geometry of the oxygen atom is tetrahedral when we consider all of the bonding and electron domains. The net dipole moment is shown in red and bisects the two lone pairs. We only consider the bonding pairs. Now this means that there is a net dipole moment as the electron density is being shifted towards the more electronegative oxygen. And the molecular dipole, the sum of the bonding dipoles, is not equal to 0. So this means they don't cancel out.
This concludes part C.
In this video, we're going to focus on the types of intermolecular forces and how these affect the solubility of organic compounds in water. So let's get started. Off the bat, many students get confused between the terms intra and intermolecular forces, so it's worthwhile making this distinction up front. Covalent bonds and other intramolecular forces, we'll discuss more of those on the next slide, usually are between the individual atoms of a molecule or ions from a formula unit. However, an intermolecular force is one between molecules and is highlighted here in red. The distinction is that the intermolecular forces are usually the ones that affect the physical properties of many molecular compounds, and they are typically much weaker than any of the intramolecular forces. So, for example, a covalent bond. An obvious comparison is by considering the energy that's required to overcome these intermolecular forces with that of intramolecular forces. So let's take a look at that now. As a quick recap of an intramolecular force, these are the ionic and covalent bonds. And so in ionic bonding, the basis of attraction will exist between the electrostatic attraction of a cation for an anion. And these typically require anywhere between 400 to 4,000 kilojoules per mole to break apart these bonds. They're incredibly strong. So the other type of intramolecular force is the covalent bond, and the basis of attraction is the sharing of electron pairs. Now these can differ in energy anywhere between 150 up to 1100 kilojoules per mole of energy required to break these ones. So all in all, these are much stronger bonds, and they exist between atoms. Let's now have a look at some of the intermolecular forces. Here's a really nice summary slide that shows all of the possible intermolecular forces that can exist either between an ion and a molecule, or in fact two molecules. So the one thing to note from this slide is that all of the energies required to break apart these intermolecular forces are much lower than the energies that are required to break apart intramolecular forces, that is either an ionic or a covalent bond. What we're going to do now is we're going to take a look at some of these forces in turn and talk about how they will affect solubility. For the remainder of this video, we're going to consider the physical property of solubility and how these intermolecular forces play their part. So the first question that we're going to answer is going to be about sodium chloride and its solubility in water. In order to understand this, we need to recognize that each ion is held together in a regular lattice, and that the forces of attraction, the ionic bonds in this lattice, will need to be overcome so that each ion can be solvated, or in this case, because we're using water, hydrated. So the attraction between the water and the individual ions will pull apart this lattice as this forms new attractive forces, and we'll see these on the next slide. The lattice structure of salt is pulled apart by the formation of new ion dipole forces between sodium ions, chloride ions, and the water molecules. Water molecules, by virtue of their high polarity and compactness, are able to entirely surround each ion as it is freed from the lattice. The energy supplied by the formation of these forces is great enough to overcome the lattice energy and interionic attractions of sodium chloride crystals. Another argument for this is that the more ordered and regular lattice is disrupted, and each solvated ion represents a favourable change in entropy, as the solution has more disorder than the regular structure of the crystal lattice. Let's now consider another very strong intermolecular force that also helps water to dissolve organic compounds. The next discussion that we're going to have is concerning hydrogen bonding, and seeing as water is our solvent of choice, let's think about the hydrogen bonding that exists between water molecules. In fact, without water's ability to form these hydrogen bonds, none of the water on this planet would be a liquid, and life as we know it wouldn't exist. So, are there any other types of hydrogen bond that you need to be aware of? Let's find out. There are two components of a hydrogen bond. That is the hydrogen, which is the hydrogen bond donor atom, and there is also a hydrogen bond acceptor. The hydrogen bond acceptor is the lone pair that is on an electronegative atom. So when we're talking about hydrogen bonds, these will include hydrogens that are bonded to oxygen and nitrogen, but can also include those atoms bonded to fluorine. Hydrogen bond acceptor atoms include the electronegative atoms nitrogen, oxygen, and fluorine. Now the name is a bit of a misnomer. These are not bonds per se. Remember, these are intermolecular forces. To avoid the confusion, always represent a hydrogen bond between the donor atom and the acceptor atom as a dotted line. I'm including an example of an alcohol on the next slide that is hydrogen bonded to another molecule of itself and to a water molecule. The OH group makes the alcohol hydrophilic, and hydrophilic means water-loving. As the carbon chain is quite small in this alcohol, the water is able to hydrogen bond with the alcohol group, and the alcohol can also hydrogen bond to other molecules of itself. When this happens, the alcohol becomes dissolved in water. When one liquid dissolves in another, we refer to the solution as being miscible. However, this miscibility has got limits, as we'll see in future slides. A general rule of thumb here is that hydrophilic solvents will dissolve other hydrophilic solvents, and that hydrophobic solvents will dissolve other hydrophobic solvents. So an example of a molecule that is hydrophobic would be a straight chain alkane such as hexane, which is the principal component of petrol. Unlike the alcohol, hexane would be immiscible and forms a bilayer when these two liquids are mixed together. Let's consider now the molecular model of this behaviour. You probably knew long before I told you that oil floats on water, so what a better explanation for this? Well, a better explanation is that in order to get a substance to dissolve, there can be an entropy argument whereby a species moves from being in a more ordered state to a less ordered state. This we saw when we discussed sodium chloride. But when we think of hexane being dissolved in water, what are we really asking water to do? Well, if it's going to form a hydration sphere like it did in the case of our sodium chloride, then each water molecule would have to surround every molecule of hexane. And this would form a more ordered, not a less ordered system. Hence, this involves an unfavourable entropy change in dissolution, and hexane is insoluble or immiscible in water. I'll not spend too long stressing this, but polar solvents dissolve other polar substances, and again this has everything to do with the types of intermolecular forces that hold these mixtures together. Other than alcohols with short carbon chain lengths, another group of organic compounds that dissolve in water are the carboxylic acids. These can form hydrogen bonds with each other and not just water. Note that the dashed line is not a bond. In fact, hydrogen bonds are often longer than the usual bonds that connect the oxygen and hydrogen. This is why I decided to include the space filling model, which focuses on just the interaction between these two molecules of the identical carboxylic acid, ethanoic acid. If you like vinegar on your chips, then you've definitely smelt this, but the vinegar on your chips is way less acidic than this compound. Both of the bottles that are on display on the top right of your screen contain acetic acid, which is the old name, or ethanoic acid, the new name. But note how one of these bottles is clear and the other one contains crystals. Why is this? Well, in the clear bottle of acetic acid, the hydrogen bonds occur between water and the acid. Note there is an additional hydrogen bond acceptor atom on the acetic acid that we haven't covered yet. Where is this? Pause the video and study the diagram. Press play when you think you have an answer. The other hydrogen bond acceptor atom is the carbonyl oxygen of the carboxylic acid. So why does the other bottle have crystals? This is because the glacial acetic acid forms crystals when the carboxylic acid bonds to itself rather than water. And in fact, that tells us there's very little water content in glacial acetic acid, so at low temperatures, the crystals take on a glacial appearance, hence the name. You certainly wouldn't want to put this on your chips. What about if we increase the hydrophobic portions of these highly soluble compounds? How far can we push it? Adding one more carbon to ethanoic acid gives us propanoic acid, and hydrogen bonding can still occur as the hydrophobic effect of increasing the carbon unit by 1 does nothing, and so this is still soluble. What about if we add another carbon? Now if we add one more carbon to the chain, doesn't make that much difference either. Butanoic acid is still soluble in water. However, if this was butanol, which was the alcohol version, here we would see some sparingly soluble behaviour starting to occur. By adding an additional 2 carbons to this chain length, we've really started to push our luck. The pentyl chain is in effect non-polar, and so this begins to affect the solubility of our carboxylic acids, and very little of this will dissolve. With other functional groups such as alcohols, the size of the carbon chain is usually less, so typically 4 to 5 carbons before those alcohols become borderline soluble. So let's think about increasing the carbon chain length by another 4 atoms and see what happens now. At this point, there's no chance of this carboxylic acid being soluble whatsoever. The other earlier carboxylic acids, though, were only sparingly soluble. In addition to this, unfavourable entropy wins the day here, and there is no way of forming a solvation sphere around such a long carbon chain. But what about other polar molecules which contain 6 carbons? I think of one that we use on an almost daily basis, glucose. Our sugar molecule, despite having 6 carbons, also has a large number of OH bonds or alcohol groups and that ether bridge at the top. All of these make it possible for sugar to dissolve, as this increases the number of hydrogen bond sites with water. After all, sugar is a polar molecule. So even though it has a lot of carbon atoms, does this mean that it will dissolve in hexane? No, of course not. Sugar is a polar non-electrolyte. Like dissolves like. Sugar is polar, hexane, well, isn't. Therefore, a very polar molecule will not dissolve nor mix with a non-polar solvent like hexane. When two molecules with a dipole interact weakly, these will form dipole-dipole interactions, and these are held together by dipole-dipole forces. Now, if there are enough of these forces, then solubility or miscibility will still occur. Here we have two small polar molecules, acetone and chloroform, and we can see that these are being held together by dipole-dipole interactions. The carbonyl oxygen has a partial negative charge, whereas the carbon hydrogen gives the hydrogen a partial positive charge. That partial positive charge on hydrogen results because it has 3 surrounding carbon-chlorine bonds that are withdrawing the electron density from that carbon-hydrogen bond. So I know I said that carbon-hydrogen bonds aren't particularly polar, but there will be an electron-deficient hydrogen at the other end of that molecule. So all of these molecules are then able to align and have dipole-dipole interactions, which are dipole-dipole forces holding them together. Other types of interactions also include the dipole-induced dipole interactions and the dispersion forces, but these are typically when there are non-polar molecules being mixed together.
This concludes Part D.
In this video, we're going to look back at some intermolecular forces we've already covered and add some new ones. However, we'll change tack and consider another important physical property that is often used to separate mixtures of organic compounds, that is, boiling points. In our first example, we consider the ion-ion electrostatic interactions and really the futility of a boiling point for this particular intermolecular force. Ionic compounds usually require hundreds of degrees to melt, and this melting point is typically defined as between the well-ordered crystal structure and the random liquid state that we see in our diagram on the right. Now, sodium acetate is an organic salt which, once you've melted, is more likely to decompose before it boils. Now let's confine our conversation to compounds that can boil without decomposition. And for this, let's think about the uniqueness of water once again and its predominant intermolecular forces, the hydrogen bond. In order to get water to boil, you have to put in a lot of energy, hence it has a very high boiling point. Note that 100 degrees centigrade. However, when you look at this, water has got a fairly low molecular weight. It's only 18. If we change the oxygen atom to a sulfur atom, then we almost double the molecular weight. However, note still that hydrogen sulfide, because of its inability to form hydrogen bonds, even though we've doubled the molecular weight, the boiling point is over 140 degrees lower. When we think about the molecular weight of water and compare it to, say, methane, which has a similar molecular weight of 16, then we can see already that there is a huge importance of the hydrogen bond in determining the boiling point. If water was not able to form those hydrogen bonds, then at room temperature, it clearly would be a gas, and all life on Earth just wouldn't exist. Organic molecules are also capable of hydrogen bonding, as we saw in the previous video. But how might this affect a homologous series of compounds? Let's take a look now. When we consider the simplest alcohol, that's methanol, then we can be drawn into a trap here in that thinking that hydrogen bonding between these units are always going to be responsible for the increase in the boiling point of this series of compounds. I mean, sure, for the smaller members of this group, methanol, ethanol, propanol, then these are going to hydrogen bond with each other more readily. And in addition to that, we can't ignore the fact that there are other intermolecular forces at play, which we'll be talking about later during the course of this video. And these are dispersion forces. And these actually become more important than the hydrogen bonds the larger the hydrophobic portion of our hydrogen bonded substance is. So this could be amines, it could be alcohols, it could be carboxylic acids even. And really what I'm trying to provide here is an early warning system in getting you to realize that it's never going to be only one type of intermolecular force that governs the boiling point of a substance. Usually these effects are additive. The last type of intermolecular force under discussion is the London force. Sometimes you'll hear this referred to as a van der Waals force or a dispersion force. Now these individually are very weak, but there's usually an additive effect whereby when there are enough of them, they can actually end up being the predominant force that holds together molecules and is responsible for the increase in the boiling point, despite there being other stronger intermolecular forces such as hydrogen bonds. How these molecular forces actually arise are that two molecules will approach each other and the electron cloud of one of these molecules will result as they're moving around. We refer to these as being momentary dipoles, whereby the electron density shifts in the molecule. As this molecule continues its approach towards another molecule, then the electron density of the blue molecule is shifted towards the left, and that's because the green molecule with its momentary dipole causes a change in the electron distribution of the blue molecule. We refer to this now as being an induced dipole because the momentary dipole induces or causes a change in the other molecule. So the next thing that happens is that there will be an attraction as seen on the next slide. We call this a momentary dipole, or we will call this a London force or a dispersion force. And this happens because the electrons are always on the move, so therefore the attractions are also only momentary. Now there are a couple of factors that can affect this force of attraction, and the first of these is the surface area. When we think of dispersion forces, the danger again is to think of these as being just very weak, and that can be wrong because the surface area and the molecular weight of a molecule, which is directly correlated with surface area, can increase the size of the force because there are more electrons involved, so more dipoles set up, and therefore a greater force of attraction to overcome in terms of boiling. When we think of the fractional distillation of crude oil, which is a mixture of all types of hydrocarbons of all sizes and shapes, these are nonpolar molecules which would be held in a liquid by a dispersion force, and they range from gases to liquids with boiling points over 400 degrees Celsius. So there's got to be a wide range of strengths of the dispersion forces, from the very weak in the gases like methane to the relatively strong in the sort of hydrocarbons that end up in products like bitumen, which we use to coat the surface of roads. So as the molecule on the right with the larger momentary dipole is set up, this is going to induce a dipole in the other molecule on the left, and as a result of that, has a bigger intermolecular force of attraction, which of course then affects the boiling point of a substance. Let's take a look at some examples now. Here's a sequence of moderately sized molecules which demonstrate the additive effect that I'm trying to get across here. All of the molecules are nonpolar, so dispersion forces are the only intermolecular forces of attraction between each of these compounds. The circles in the centre of the benzene ring simply mean that the pi bonds are delocalized over the whole ring structure. That is, the electrons don't belong to one particular atom, rather they're shared over all 6, which means there's a very large pi cloud. Notice that every time you attach another benzene ring, then the boiling point goes up by about 140 degrees Celsius. So by the time you've got to anthracene, the boiling point's really high. Since this is only because of dispersion forces between the molecule, we can assume that those dispersion forces are really strong. Now I've chosen this particular example because benzene's nonpolar and the delocalized electrons make them very polarizable, giving rise to temporary dipoles very readily. Lastly, another factor worth considering is the points of contact argument. All of these molecules are flat, so they can lie closely together. The polarizability and the fact that the molecules can lie closely together help to make the dispersion forces strong. However, what if we introduce some branching in a straight-chained alkane and change the surface area in this fashion, but keep the number of electrons and the molecular weight the same? Here we have some structural or constitutional isomers of pentane. The space-filling representations allow us to see the effects of how changing the shape of a molecule affect its surface area and how this will impact the number of points of contact between each of these individual molecules. Let's see if we can now account for the boiling points. If we look at the two ends of the spectrum, we have pentane, which is a straight-chained alkane, and we have 2,2-dimethyl propane, which is a branched or a heavily branched alkane. And the pentane molecules will be able to come in close enough contact with one another to form numerous points of contact and numerous temporary dipoles. This means there's going to be more dispersion forces, and so with more dispersion forces available, then more energy is going to be required to overcome those intermolecular forces and get pentane to boil. Conversely, as we've just said, the 2,2-dimethyl propane, well, this has a lower surface area, therefore there would be fewer points of contact, and as a result, fewer temporary dipoles, and therefore less energy would be required in order to overcome the intermolecular forces. Lastly, I'm not ignoring dipole-dipole forces. I've just been waiting to have the prior discussion before deciding to include this final portion. When we make comparisons, it's better to keep the molecules the same where possible, so approximate molecular weight or numbers of electrons, which is exactly what I've done in this last example. When one considers fluoroethane and ethane, the molecular weights are similar, but we might imagine that carbon-fluorine bond having this huge effect on the boiling point. Well, let's consider that for a moment. Certainly fluorine is the most electronegative element, and therefore carbon-fluorine bonds are going to be incredibly polar. However, even given the large permanent polarity of the molecule, the boiling point has only been increased by 10.2 Kelvin. Now look at it like this. If there are no intermolecular forces at all between the molecules, everything would just boil at a temperature that's fractionally above 0 Kelvin. Not actually at 0 Kelvin, because there has to be a little bit of energy to enable some movement. Now in ethane, the dispersion forces are strong enough that the boiling point has been increased to 184 Kelvin. Now when we add the effect of that permanent dipole-diamond dipole interaction to that, the only extra difference that that dipole-dipole attraction has made is to increase that boiling point by 10.2 Kelvin. And this really is negligible compared with the effect of the dispersion forces. You can't say that dipole-dipole interactions are stronger than dispersion forces. Part of the problem with this example is that the fluorine is so electronegative that the electrons in the carbon-fluorine bond are pulled very firmly towards the fluorine atom. So that makes the molecule much less polarizable and so reduces the size of the dispersion forces, which depend on that temporary movement of the electrons within its molecules. So there are two effects operating in opposite directions. That's the polarity of the carbon-fluorine bond is adding dipole-dipole attractions, while at the same time, the more tightly held electrons are reducing the effect of the dispersion forces. So the two boiling points are pretty much the same. That means that the gain in dipole-dipole attractions is roughly cancelled out by the loss of dispersion forces. So be careful. When making comparisons, don't simply ignore the weaker forces. Appreciate that they are there too, but there might be additional intermolecular forces that have some effect on the boiling point.